independence. So first I'm going to start with the scenario that is listed here. I'm on page 14 in your notes, and then just go ahead and put the date up there at the top of your screen. All right, so my scenario is let's say that I flip a coin. What's the chance of getting heads? What's the chance of getting tails? We've seen this a million times before. Those are both 1/2. Now I'm going to make a new assumption here. Let's suppose, and the extra information I'm going to give you today is that your first flip was a tail. What if you flip that same coin again? What's the chance that my second flip is also tails? Well, the coin doesn't care about what the first flip was. The chance that my second flip is tails is going to be exactly the same. It's going to be 1/2. So knowing that extra information, knowing that I had a tails in my first flip, had no impact on the probability that I get tails for my second flip. This is what's called independent, and I have the definition of independence on there. Definition is if I know that an event has occurred, it's not going to change the probability of a second event occurring. So we're going to have some tests that we'll use to check for independence, and I'll talk about that here in just a second. Let's think about our suppose the flip was a tail. That's the extra information I'm giving. I don't care if the first flip was a heads or a tails. Knowing this one event occurred doesn't change the chance that I got tails on my second flip. What we're going to do to test for independence is we're going to check two different equations. They both have to be true if you want to have events that are independent. And so what I'm going to do is I'm going to check the probability of A given B. Now this given here, I'm given extra information. This is the knowing that one event occurred. Knowing that B has already occurred should not change the probability of A. So the probability of A given B should be the same as the probability of A. A doesn't care whether or not B has occurred. Now, the other thing that has to be true is the opposite. I want to figure out the probability of B given A. B should not be affected by the chance that A has occurred. So the probability of B given A should be the same as the probability of B. We're going to look at two examples down here to check for independence. Now, I am going to caution you when you're looking at independence. It's really easy to read the question and say, I think that those things would be independent. And unfortunately, that's not the way things work because probabilities can be really deceiving. So you do need to check these formulas here and use those to decide if things are independent. Don't just think about the question. You really should check it with the formula. All right, so let's look at these two examples down here. We're thinking about choosing cards from a standard deck of cards. And I'm going to define two events here. The first event is that A is the first card is a heart. Event B is that the second card is a heart. So what I would, if you don't remember what's in a standard deck of cards, what I'm going to suggest that you do right now is just Google the cards in a standard deck so you can sort of see the breakdown of each type of card. And so we're going to look at these two examples here. And actually, I want to start with example B. So I'm going to kind of do things a little bit backwards. So we're going to shuffle a standard deck of cards and turn over the top two cards one at a time. Are events A and B independent? So I'm going to check my two equations there. And actually, for the purposes of this question, I'm going to start with the second one, the probability of B given A. And I want that one equal to the probability of B. Now, I want you to keep in mind, both of these things have to be true. So if I'm checking this equation and the first one works, the first one is true, that doesn't give me evidence that my events are independent. I have to check the other one as well. However, if I check it and this first one doesn't turn out to be true, that's good enough to say, no, these events are not independent because half of the equations didn't work. So if we get something that doesn't work out, we're done. If we get something that works out, we will need to check the other option where we flip them around. Okay, so what I am going to actually also do, I have my equation written down there for part of 15b. However, I don't necessarily know that that's going to be true. So what I'm going to do is I'm going to put quotes around my equal sign. Sometimes you'll also see an equal sign with like a question mark above it. And what that means is that I don't know that these are true. So it's going to help us kind of differentiate between equations that we know are true and we're using these equations to help us solve the problem versus something that we're testing. And in this case, I don't necessarily know that these are true. I'm just testing because I want to see if it's true. I want to know if they're independent, as opposed to being told that they're independent and knowing that this formula is true. So you're going to see me put the little quotes around it because, like I said, this is something I'm just still trying to test out. I first want to turn this into words. The formula is great and all, but really we need to use the words of the events. If it makes sense to you to keep it in terms of A's and B's, you absolutely can. but I'm going to turn this into some words here. So the probability of B given A, that's going to be the probability that I have my second card is a heart, given that my first card was a heart. And I want that potentially equal to, so I'm going to put my quotes up above, the probability that my second card is a heart. I'm sorry, the probability that my second card is a heart. Yeah, okay. All right, so there's what we kind of have there. So what I want to do now is I'm going to use my conditional formula to turn this into our other sentence here. So in the numerator, I want both of these two things to be true. So that means that my second and my first card both need to be hearts over the probability that my first card is a heart. And again, I want that potentially equal to the probability that my second card is a heart. Okay, let's figure out what these actually are. So I'm going to do that over here. So I kind of have my setup there. All right, let's look at the numerator on the left side. If I want my second card and my first card to be hearts, that means I get hearts and hearts. Now what I'm doing is I'm taking my cards and I turn over the top card, I put it to the side, then I turn over the next top card and then I put it to the side. So if I just turn over one card, what's the chance that my first card is going to be a heart? So for my first card to be a heart, I have 13 options. There's 13 hearts in a standard deck. There's 52 cards that are available to me. I'm going to multiply this, and I'll talk about why we multiply a little bit later. So my second card to be a heart. In this scenario, my first card was already a heart. So I took my heart and I placed it over to the side. If I consider what's left in my standard deck of cards, there's not 13 cards left, there's 12 cards left in my standard deck of cards. And there's not 52 cards, there's 51 cards left in my standard deck of cards. Now in my denominator, I want the probability that my first card is a heart. I've already found that. That was the 13 out of 52 that I had before. Okay, so there's that side. Now let's look at the other side of the equation, the right-hand side. In this case, I don't care what the first card was. I only care that my second card is a heart. This one's going to just get a little bit complicated here, so I'll put this one in here for us. This one's going to be 13 out of 52 plus 12 out of 52. So just kind of keep that, just write that on your thing. We're going to talk more about how I got those values later, but it's not important for right now. Okay, so what I'm going to do is I'm multiplying here. I see the same fraction on the top and on the bottom. So here I have 12 out of 51 potentially equal to 13 out of 52 plus 12 out of 52. Are those going to be the same? They're not. Okay, so this is definitely not going to work out. We got something that didn't work out. I don't need to check the other side. A and B are not going to be independent. And I can say this for part B, not independent. Okay, let's look at part A. So the difference between part B and part A, part B, I'm not putting my card back in the deck. I just turn it over and then I turn the next one over. Now in part A, I turn over the top card. I look at what the top card is, then I put it back in the deck. This is really, really, really important. Okay, this has really big consequences for us. I'm going to shuffle them up again, and then I'm going to turn over the top card again. Now I want to know if A and B are independent. So let's just check the other side. We checked the B given A. I'm going to check A given B for this one first. I want that potentially equal to the probability of A. So let's put this into words. This is going to be A is that my first card is a heart, given that my second card is a heart. And I want this potentially equal to the probability of A, which is that my first card is a heart. Okay, let's go ahead and use our conditional formula. So now I'm looking for the probability that my first and my second card are both hearts over the probability that my second card is a heart. Again, potentially equal to the probability that my first is a heart. Okay, so let's go ahead and find these in math values. I'm going to change my color so we can put our fractions in there. We need the first and the second card to be a heart. Well, in my first card, I have all 13 cards available to me. All 52 cards are in the deck. Again, I'm going to multiply. For my second card to be a heart, well, I've put that first heart back in the deck. So all 13 cards are still available and all 52 cards are still in the deck. It hasn't changed because I was able to put that card back in the deck. In my denominator, I want my second card to be a heart. The first card can be anything. So I'll put a 1. It can be anything. It doesn't matter what the first card is. The second card to be a heart is always 13 out of 52 because whatever I get for that first card, it's going back in the deck and I'm shuffling it around. I want this potentially equal to my first card being a heart, which we already determined was 13 out of 52. Okay, so we see a lot of 13 out of 52s. These ones are going to cancel out. I get 13 out of 52 is truly equal to 13 out of 52. That's good news, you guys. We got something that worked out. I will tell you that if you flopped those two things around, the probability of B given A is also equal to the probability of B. Let's not do that today, although you're welcome to check it if you want. We should get that the first one is independent and the second one is not independent. I could have told you this right from the beginning. So a good rule of thumb for us, and this is always going to be true, and I make a little note on here somewhere. Anytime we're sampling with replacement, which is the case of the first one, we took the card out, we looked at it, we should put it back in the deck, and we shuffled, and then we drew it again. It's that putting it back in the deck that tells me I'm replacing the card after I choose it. Those are always going to be independent. However, anytime you're sampling without replacement, which is the case of the second one, we don't put that first card back in before we choose our second card. Those are never going to be independent. And this is a rule of thumb, and you are 100% okay to say, I am sampling with replacement, therefore it's independent. Or vice versa, I am sampling without replacement, therefore these events are independent. If you are not told this, and if it asks you to kind of check things mathematically, you can use the two formulas, again, keeping in mind that they both do have to be true.